Hello, I'm Giovanni Camurati.
And I'm Marius Münch, and as introduced, we are here to talk about screaming channels. Sorry for the small delay, there were some technical problems, but now we start right ahead.
Yes, we are two PhD students in Eurocom. It's a university in southern France, in Côte d'Azur. And we did this project with our colleagues Sébastien Peuplao, Thomas Hayes, and our supervisor Aurélien Transceivers.
But I can imagine a lot of you here came to the room, maybe read the abstract, something about AES, 10 meters, side channels attack. So let's just get you in the mood. Like, what is this talk going to be about? What will you hear and see in the next 45 minutes? So first of all, it's about a new kind or a new way of electromagnetic side channel attacks possible from a distance. It's about our story, how we got there and how we discovered it and how we made it working in a distance up to 10 meters, which we will explain later why it is impressive. And we will even have like a small demo set up here, which we will show. And last but not least, we are going to tell you where to go from here, what to do. But let's start from the beginning. So, as we know, nowadays life is mostly more dependent on RF communication and in a lot of small devices with the rise of the so-called Internet of Things and similar things. So imagine, for instance, you have a smart lock and your phone, and you will just, come home, pass with your phone, and the smart lock will identify your home and open. Obviously, there's not much magic involved in the end. Like, there's, at the end of the day, on the smart lock, just an ordinary microchip.
Yes, and one of the most popular architectures for those kind of chips is the so-called mixed signal architecture, in which, as you can see in the image, there is the digital logic, the processor on which the application software is running, on the same silicon die as the radio, the analog components of the radio, for some popular wireless protocol. For example, in this example, we have a Bluetooth communication with the phone. But once we have a channel, we also want to secure it. So we want to run some encryption, for example, AES, software AES. And as we know from conventional side channel attacks, running such software produces noise, which is actually correlated with the data being processed. Here you can see, for example, signature of AES with the key schedule and the first round. But what is special here is that because of the close physical proximity between the digital logic and the analog logic of the radio, this noise flows from one side to the other because there is some path between the two. So it is picked up by the radio and it is eventually transmitted over the air.
And that this noise is transmitted and contains some sensitive information is the new part about screaming channels in the end. Like, just that we abuse it, that we sit on the other end or with our software-defined radio, some signal processing software, and in the end get out the secret key used for the encryption on the device. And please note here, the device doesn't have to send any encrypted message at all. It's enough that the device encrypts while sending. And that's more or less the high-level overview about screaming channels, but now let's go from the beginning in a little bit more of detail.
Yes, and to understand all our project, we need some background that we will give you. So let's start with something on side channel attacks.
Exactly. So I guess probably the most of people of you are familiar with side channel attacks. And let me just really wrap it up for those who are not. In essence, even provably secure cryptographic algorithms have to run on hardware at some point in time to actually do things, right? And one big problem we have is that hardware is not perfect. Hardware may leak, based on the intermediate computations. For instance, it has different timings or different power consumption based for intermediate values it uses during computation. And when we as attacker are able to abuse it and construct some signal or some original cryptographic secrets out of this data leaks or leaks over side channels, we speak of a side channel attack. And just to put it in context, one very famous device used to carry out side channel attack, who knows what this is? Hands up. Yeah, exactly. It's a chip whisperer. And we use it also, or we use software of it also for our attacks. So just some notion here. Okay.
Yes, but how does the attack actually work? How can we recover the key from this noise? So we will present So, sorry. We will first give you some basics of electromagnetic side channels. Go, Mari. Sorry, my fault.
Oh, what? Sorry, that's why.
That's the electromagnetic.
I don't see.
Okay, so the idea is that electromagnetic side channels are one of the types of side channel attacks, and the idea is that because logic switches, it consumes currents, and current variations produce some electromagnetic fields that we can try to use to attack. And we will not be really exhaustive, but we want to give you a few example of attacks, just to give you an idea of what's possible up to now. So, for example, on smart cards and laptops, we can do attacks at about 15 centimeters of distance. And there is a very famous attack called Tempest on monitors. Here we can recover what is being projected on the screen up to 5 meters. But in this case, it is not an attack against cryptography. It's just recovering, but it's recovering the image projected on the screen. But how can we actually recover a key when we perform a side channel attack? So one of the simplest attacks that we can imagine is the so-called correlation attack. There are many more. And let's see, what do we need to do that? So first we need to know the plain text, or also the ciphertext would work. Then we need a nonlinear relationship between the key, the plain text, and some internal state of the algorithm, some internal computation. So let me give you an example. This is the first round of AS, and you can see a byte of the plain text, which is XORed with a byte of the key and enters a highly nonlinear function called sbox, and its output is the state. Then what we need is a linear relationship between this state and the leak. So for example, if we measure the electromagnetic side channel, or if we measure power consumption, what we measure will be somehow linearly correlated with this state. And this relationship between key, plain text, and this internal state, it's what we call the leak model, because it lets us predict which will be the leak for a given computation. But let's now try to actually perform the attack step by step. First, we need to encrypt many times with known plain texts and collect the corresponding leaks, as you can see in the scheme. Then we want to guess 1 byte of the key, as you can see here. And once we know this guess, the plain text and the sbox, we can compute the values of the state for this guess. And then to decide whether this guess was correct or wrong, we can just check the linear dependency between the measured leak and this guess, this computed guess. And if the guess was correct, well, of course, they would be linearly correlated. And if instead the guess was wrong, since the sbox is highly nonlinear, a little mistake in the guess would produce a big mistake in the computed values. Here we tried to represent it by shuffling the colored squares. So they're shuffled, they are not linearly dependent with the leak anymore, and we can then see that this key is wrong. So to complete the attack, we just need to repeat this for each possible value of the guess and for each possible key. So here is the algorithm. For each byte of the key, for each possible value of this byte, we compute the correlation between the leak and the guess that we computed, and we choose the one which has the best correlation as the best guess for our byte. And what I want to point out here is that since we are attacking step by step, byte by byte, the attack is manageable in complexity. And that's possible only thanks to the leak, which gives us an insight on an internal state of the algorithm, which is instead secure if we look at it from a mathematical point of view as a whole.
But now let's move on to a different kind of background, like completely different, a little bit about RF communications. So this is a sine wave, pretty easy. It like moves over a distance, over time, and it has a certain amplitude, which is like the peak of the wave, and the distance between two of those peaks is called the wavelengths. And how waves are propagating is traditionally calculated like lambda, the wavelength, is equals velocity divided by the frequency. And as we're dealing with electromagnetic waves or radio waves, RF waves, the velocity is just the speed of light c. So we can directly see a correlation between the wavelength and the amplitude. Another way to look at the wave is in the power spectrum. So there we will have the frequency aligns on the x-axis, and depending on how high it goes, the more intense is this frequency in the spectrum over different frequencies. Important to know for the rest of our talk is a little bit how modulation works. So basically, the main idea of modulation is you have information, like in this case, an analog information, which you somehow want to transmit over the air. So what you will do, you will put a carrier wave, which is just one cyclic, very boring wave. You will generate it with an oscillator most of the times. You mix those two together, and at the end, you have, in this case, an amplitude modulated wave, looking somewhat like this. So you have the information signal modulated over your carrier wave. And in the power spectrum, this looks kind of interesting, because now you don't even only see the carrier wave, but also the information signal on the side of them at a certain offset. So that's just a very, very brief introduction to RF for understanding later graphs in our presentation.
Yes, now we will give some background on mixed signal chips. Mixed signal chips are extremely popular. They are in many devices for many wireless protocols. For example, I brought here a smartwatch, and it's using Bluetooth, and most likely it has a mixed signal chip in it. And also other devices like presenters or keyboards, and many different technologies. And why are they so popular? Well, they're so popular because the idea of combining the digital logic and the analog radio on the same silicon chip has a lot of benefits, a lot of advantages. It is power efficient, it is easy to integrate in larger systems, because the developers can just take this single chip with a single SDK and program their application and have access to very power efficient and cheap radio for wireless communication. But unfortunately, the designers of such systems have to face a big challenge, which is noise. And why? Because digital logic is by nature very noisy. It's very noisy because values are switching between zeros and ones, and from an electrical point of view, these are extreme values, and sharp changes produce spurious emissions. Then the close proximity, the short distance, the fact that digital logic and analog logic are built on the same silicon die facilitates the propagation of this noise from one side to the other. And unfortunately, the analog components that made the radio are very sensitive, again, by nature, to noise. And I want to point out that we are talking about modern digital wireless protocols, but still the components that compose the radio are analog components, and they are sensitive to this noise. So the designers of those chips have to make sure that the radio still works even in presence of this aggressive digital part. But our hypothesis was, what about the actual information that is present in this noise? Let's not just think about it from a functional point of view, let's think about it from a security point of view. So what if this sensitive information is picked up by the radio, transmitted, and we can perform a side channel attack from a large distance, larger than before?
Yeah, so we had this idea, and that's basically a little bit like how our journey began. But we didn't know where to start checking, because there were just so many different variables. Like, for instance, what kind of devices should we look at? Should we watch at Bluetooth devices, Wi-Fi devices, GSM? What kind of firmware should they run? Should we look for hardware AES encryption or software encryptions? What kind of how would the noise propagate? On which amplitudes, or is it on the amplitude? Is it in the phase of the signal? Is it on certain frequencies? So we really had a lot of things to test out and then to figure out, and it took us a while. And after a couple of months of really trying around, we have tried out several chips, several things. We came up with a custom firmware just to prove like basic things working or not. We found accidentally one of those leaks. While accidentally, well, we just tuned on the wrong frequency. We did some math wrong and ended up listening on the wrong frequency, and suddenly there was a leak, which we could observe, and this leak was dependent on our computations. Amazing. So let's have a little look at it, how it looks like. So this was more or less our setup. We had a firmware which called transmit or not transmit in a continuous wave mode. So this is basically a test mode which will just send out one wave, no actually packets. The chip which we used in this scenario was a popular Bluetooth chip. And we will just, inside the firmware, like trigger different loops, like either a fast loop or a slow loop, as we call it. And the fast loop, or the slow loop is basically the same as a fast loop with some additional knobs in between to just spend more time before the loop actually reiterates. And yeah, this would be controlled over serial. And what we saw is something like that. Like on some sidebands of the 2.4 gigahertz spectrum, which is like the main Bluetooth frequency, we saw those kind of leaks. And we wanted to see what's going on. So what we did first is we took a spectrum analyzer, so a device which would put us the full power spectrum and not just some sidebands or some close bands, so like a normal software-defined radio, and hook it up very close to the device, to our Bluetooth chip communicating. So what we will see first, if we run the different loops, we will see that the red arrows here, like the leaks, are moving depending on which loop is running. And if we now would put the spectrum analyzer farther away, we would also, oh, of course, sorry, I forgot to mention that. That was the conventional electromagnetic leak we saw there. And if we now go farther away, we can see the same leaks happening from a distance, and at the 2.4 gigahertz band. Like it's behaving exactly the same as a traditional electromagnetic side channel leak. So with that, we could actually start and trying to understand what was going on here.
So what we figured out is that there are two main modulation stages. First, the loop is spinning at a fixed frequency, so it's producing a noise which has a fixed frequency component. That's the red arrow you can see in the leftmost spectrogram. And this digital noise at a fixed frequency, it's somehow mixed with the clock signal of the chip at 64 megahertz. So what happens is that this clock is modulated by the noise, and in other words, the noise is brought up to 64 megahertz, and you can see it in the second spectrum plot. And what's special in streaming channels is that this noise, because of the proximity between the two parts, flows to the analog radio, and here it is mixed once more. And this time it is mixed with the carrier of the protocol, and in this case we have a Bluetooth carrier at 2.4 gigahertz. So this carrier is modulated, or again the noise is brought up to 2.4 gigahertz. And what do we have in the end is that the information, the sensitive information, is spread all over the spectrum, as you can see. But let's now focus on the left part of the scheme, on the conventional part, the one that traditional conventional side channel attacks use. And the first thing we want to understand is why actually executing software produces some noise which is correlated with the data. Well, to do that, we have to think that in the end, software execution is the switching of some logic gates inside the digital logic of the processor. And in this slide, you can see an inverter which acts as a NOT logic function. So the output, the green output, is the inversion of the input on the left. And since this is a real physical component, we need a power supply and a ground to power it up. So let's imagine that we want to switch the output from 0 to 1. Unfortunately, this is a real physical component. On the output, we have a parasitic capacitance. And for those who are not familiar with electronics, just think about it as a reservoir, as a pot. And if we want to bring the value to 1, we need to fill this reservoir with current. So we provide some current from the power supply, and there is a spike, and the capacitance charges itself, and in the end, the output is 1. If instead we don't switch at all, well, there will be no power consumption. And if we want to switch back from 1 to 0, we need to discharge this capacitance to ground. So this time there will be no current flowing from the power supply to the capacitance. And in both cases, there is a very little parasitic current going directly from the power supply to the ground. It's not really important. But what you see in the end is that depending we are switching or not, and if we are switching depending on the side of the switching, the current consumption is different. So somehow there is a relationship between the logic values that are being processed in the program and the current consumption in the chip. And let's now try to understand why mixing occurs. There are several ways. The first one is here in this slide. You can see a data line. The data line is switching, and it switches depending on the logic values. And the frequency at which it switches, if it is switching, depends on the clock. You can see there is a memory element, a flip-flop, that is synchronized by the clock signal. So we could see this as actually the modulation between a carrier, which is somehow related to the clock frequency, and an information signal, which is saying, okay, the logic value is switching or not switching. Another way is the presence of nonlinear components in the system. So here you can see a transistor in the saturation region, and the output current, the red signal at the output, is quadratic with the voltage at the input. So if, for example, we provide a sum of two signals at the input, as you can see from the equation, at the output we will have approximately the multiplication of the two, and multiplication, mixing, amplitude modulation are all the same thing. So we will have that these components act as mixers. And let's now go to what is specific to screaming channels.
Exactly, like for screaming channels, like the important thing is that this classical leak also, like from the digital domains, propagates to the analog domain. And then it gets mixed up again by the radio and sent over the air. So how does it propagate? Like we have multiple theories, and the two most likely is that it either happens via substrate coupling or power supply coupling. So substrate coupling basically means if we do our like chips, we will use some substrate, usually silicon, which we place as a basis and put all the tiny digital and analog components on it, very simply spoken. And the silicon or substrate itself is normally not meant to be conducting because it just, there for separation, but under certain circumstances, it can propagate some noise, so be a tiny bit conducting on certain frequencies, and this is known as substrate coupling and could be one of the reasons why the digital noise propagates to the analog domain. The other reason, power supply coupling, is basically the idea that they could be, for instance, like very obviously connected to the same power source. So if one part consumes a little bit more of power, you would see reflections on that on the analog part as well. Note here, like this is very like the most obvious thing, like power supply coupling can also happen on different other levels. Like for instance, we are even on PCB level, like farther behind in the chain. And so how does, we have this coupling, how does it get mixed into our signal, which we can pick up on the other hand? So if we would, on the other end, if we would go for substrate coupling, it's very likely that it gets picked up by the VCO, the voltage controlled oscillator, which is here in the block diagram on the very, on the very left of you, which basically creates our carrier wave for our signal coming on. Behind that, we have a mixer, and the power amplifier would amplify the full signal, the mixed signal with information to send it over the air. And if we would deal with power supply coupling, we would have the mixing in there in the power amplifier. And then there are, as I said, that are just our two most likely theories. There can be tons of other reasons which we haven't explored yet, but at least they fit our model so far. And there's for sure a little bit more to explore on how digital noise can leak over or propagate to the analog domain.
So to sum up, the noise which is dependent on the data is generated when logic gates switch. Then it's modulated with the clock signal, and then it propagates to the radio part where it modulates the carrier, and in the end we have a spectrum that looks like that with the actual sensitive information spread all over the spectrum.
And now that we know that, like, how are we actually building an attack out of it? Like, we have all this background knowledge now. How can we attack this? So remember the firmware from early on? We modified it a little bit so that it now, besides running in simple loops and be able to transmit a continuous wave, to also transmit like ordinary Bluetooth packets over the air, and also to do AES encryptions or not. And what we here have is a waterfall plot. So we will have the signal over time, over different frequencies, and the more yellow, like one part in this plot is, the more strong is the frequency there. So if we have the radio off, like we're not transmitting anything, we don't see really much on the plot. While if we turn the radio on, we suddenly see things in the spectrum. And if we put AES on, it gets a little bit messy. So in this graph, or in this waterfall, we can see several things. So first of all, we pretty see the wait loop. Like there's just the firmware looping and waiting. So it would be like a constant signal on some frequency, similar to our custom loops we saw before. Then we see the packet boundaries. Like we see when one Bluetooth packet is stopped to being sent, because suddenly there on the spectrum is like this break. There's no signal anymore. And last but not least, we see pretty clear where AES encryption starts. I mean, before the spectrum, like even with radio on, looked kind of harmonic, and now it's just very messy, going all over the place. And if we go there and like look at one of those messy places of signal and demodulate it, we will get some graph, something like that, which is just the frequency. And we see here, like we saw after spending considerable amount of time staring at those graphs, pretty clear AES in that blue graph. Because in there we have like 10 distinct spikes, which would correlate to the 10 distinct rounds of AES in the end. So this was all pretty much manual labor, like sitting there, writing code to plot us graphs and trying to see something. And we will need for an attack to actually work to automate all the steps.
Yes, so let's see how. In the first subplot, you see the time domain. And in the second subplot, you see the same spectrogram as before, but this time it's a little bit zoomed. So in the time domain, you can clearly distinguish the packets. You see that between packets, there is no transmission at all. And with a little bit of imagination, you can also see the AES rounds. But this is even more clear in the spectrogram. And most of all, what is clear is that there are some frequency components that appear regularly before each encryption. So we could just tune into one of these components and use it as trigger. Each time it is on, it means that an encryption will start. And once we do that, we have the plot, in the first plot here, so all the traces that we have extracted aligned together. If we want to improve the alignment, we can use self-correlation between the traces. And once we have very aligned traces, there is still a lot of random noise over it. So we want to average it out. And if we average it, we obtain the second plot, which is an extremely clean trace of AES. And this was already recorded at a large distance. Now, I don't remember exactly, but maybe 50 centimeters or something like this. So you can see it's pretty clear. And once we have those clear traces, what we can do is finally perform the attack. And besides the correlation attack that I've explained before, we also use template attack. It is based on the very same leak model and the same principle, but it consists in an initial training phase with a large set of encryptions that we know, and then it works with a smaller set of attack traces. We attacked different implementations of AES. The one in embedded TLS, for example, which is protected against some forms of timing side channels, but not against electromagnetic side channels, and also tiny AES, which is a simpler version.
And the important thing, like all of this, the collection, extraction, and attacking code we made it public, open source on GitHub. Wait to the end of the talk to see the link, but you can take this and either reproduce at least the attack on traces we provide, or go out and collect your own traces. So that's pretty good, but just to give you a little bit of more visual context, like how our attack developed, like in the very beginning, we will just start like hooking up the Bluetooth chip directly via a cable to our SDR. So that's pretty close. Then we will go like 15 centimeters and got it working. Then maybe up to 1 meter or 2 meter. This is still at home, like the 2 meters at our place where we live. And well, at some point we run out of space in this place because we just had walls. So luckily we found some people which had an anechoic chamber, which was even more awesome for us because we would have like a standardized setting, a standardized room in which AF testing is done, so where there's no noise around. So we could scale up the attack pretty easily. From 3 meters, we could go up to 5 and eventually to 10. And 10 meters, what is this? I think around 32 feet. So this is pretty impressive considering that this kind of side channels before were only possible to normally attack ranges below 1 meter. So we went at least factor 10. And now it's time for a demo. So demo time. And while Giovanni sets up the demo, I will just like shortly explain the hardware which I brought. Can we have the camera on the hardware, please? Thanks. So we have here to the very left, is this from you guys? Yes. This blue board is basically just some switchable USB hub, which allows us to power switch the device behind it. It's not for the attack itself, very important, but it's a convenience feature for our proof of concept. Then up here, like the red guy, that's actually our Bluetooth chip, which we are using for transmitting, and which is just transmitting Bluetooth data. And here, to the very right, we have software-defined radio, the HackRF, which is on the low range end of equipment. And I think we are ready to go over to the demo. So to some difficulties, we just brought recorded traces instead collecting them live. So we will just show you an example with traces which we collected already beforehand, but in the very same setup, like in this fancy nice box. So so here we will see the beginning of the attack typing with different parameters. Like once again, this is open source. You can use it on your own. And here we go. It runs the correlation attack. So for every single byte of the key, it will like test all the different possible values and get the probability, like how likely this is to get the right byte. So this is running now for a while. At which byte are we currently?
11.
11. So as we are like in computer science, we are starting with byte 0. We use a 16-byte AES key. So we will wait until the script have 15 bytes. And here we are. It got correctly all the 16 bytes of the AES key used during the encryptions on the traces we collected. So yeah, that was just a correlation attack. The template attack can be checked out. And let's go on, like, where do we go from here? Like, let's conclude our talk. So first of all, let's talk a little bit about the impact of what we have showed you. So this is a pretty general problem. Like, it's not limited to mixed circuits design. It's in fact, like applicable to every kind of digital device which is close to analog radios. And I mean, this was, I think, or we assume this was already known in the SIGINT community. Remember Tempest, which we told you before? Like, this is where documents from the 80s declassified in 2000, and they speak about different kinds of how Tempest signals could propagate. So acoustics, induction, and one of the points is like modulation on an intended signal, and every other point of the is like described in the text here, and just this one point modulation of an intended signal, like where it would have to be described, there's just like the statement 6 lines redacted. So even in the declassified documents, we could find hints that, like, at least for other hardware, like non-mixed signal chips, like this could be kind of known. So now on the point of critics, right? Like you could sit there and say like, okay, you just showed us a proof of concept, you don't attack a real device, so what's the point? Why are you bothering? So, well, first, one very general thing, like attacks get only better, and we have plenty of ideas how to improve this attack and how to get there to attack a real device. Like what we have is just a very, very simple approach and a simple attack, and we could like really make the collection better because now we are over the air. So instead of just using one radio, we could use multiple, or we could make our signal processing part better because this is pretty basic stuff for you in the end. Or we just could also abuse like different weaknesses of protocols we are attacking or of protocols used by the chips which we are attacking. And last but not least, in that sense, like we really felt like sharing that very early on or as early as possible to mitigate faster, to like protect against it faster, because this changes the threat model of mixed signal chips in the end. Like where before, like where electromagnetic side channels just like on 15 centimeters distance possible, chip vendors would say like, yeah, 15 centimeters, okay, if you're that close, you can do worse things, we shouldn't care. Or we don't need to care, it's not part of our threat model. Well, now with 10 meters, it gets considerable. So we disclosed this to multiple major chip vendors and got acknowledgement from them, like they acknowledged it's a general problem and we're right. And so yeah, it's a general problem. And some of the chip vendors are even trying actively or tried actively to reproduce our results like internally, like they set up small things on their own and we try to help them with that. And some of them are even, or one, a special chip vendor is actively looking together with us into how to mitigate this in the short and in the long term and how to make things better and what are the countermeasures. Just one small notion, we don't name any vendors here because it's a general problem and we don't want to blame any specific chip vendor. But now up to the countermeasures. What could actually be the countermeasures? How could we protect against this kinds of attack?
So we could think about very classic countermeasures, software or hardware ones, which, for example, inject some kind of noise which decorrelates the measures from the data. But what we want to point out is that this may be expensive, and we're talking about very cheap, low-end and power-constrained devices. And also that once we start putting more advanced defenses, we could also apply more advanced attacks than the one we used. More interestingly, there are some countermeasures which are specific to our channel, to our new attack vector. So the first one regarding software would be to just turn off the radio while performing sensitive computations. This would just kill the channel, but at the same time, it may be difficult if there are strict timing constraints. And on the hardware side, what we could do is try to consider the security implications of noise, the actual information that is present in the noise during the design and test of the chips, instead of just considering the noise from a functional point of view.
And that's basically our talk so far. Like, let's proceed to the sound bites. Like, what can you take home from this talk? So the first and very important thing, which I think really we should keep in mind, is that everything is analog. Like, even we think of digital logic as zeros and ones, they have to, like, this digital logic in the end is just analog hardware as well, which produces noise and so on. So we have to keep that in mind for when we look at like side channels and so on, different kinds of attack.
Yes, and the last two bytes are that digital noise can leak sensitive information into the analog radio so that in the end we can perform side channel attacks from a very large distance.
And with that, we want to thank you for your attention. You can shoot questions to us like now via mail, via Twitter, later in the wrap-up room. You can see our code and more information about all of this on the links with tiny QR codes. And then you can also give feedback to this talk. And I think that's it. Floor is open for questions. Thank you.
Thank you very much.
I have a first question, perhaps.
Okay. Can we dim the lights? I don't see where you are. Okay, perfect. Thanks.
Over here.
Good.
So you mentioned that noise can be transmitted through the silicon or through the power supply, right?
Yes.
What about the actual electromagnetic emissions that are used for an electromagnetic side channel attacks? Could they? Essentially, what I'm trying to ask is, if you're not on the same silicon die, could you still have leakage onto a radio that's on a different chip but on the same PCB?
So to repeat the question, if whether like the leakage we observed is only based on the fact that the things are on the same silicon die, like that the electromagnetic emanations only get propagated over the silicon die. And I would say the answer to that, it's not like for sure substrate coupling only works on the same silicon die because it has to be on the same silicon. But for instance, power supply coupling can pretty much happen on any level on the PCB dependent on the chip design. So that could happen as well, yes.
So we focused on the mixed signal chips. We haven't tried other configurations, but they may have the same problem.
Another question here? Here?
Yep. Okay.
Yeah. So you mentioned that this is a possible exploit for Bluetooth. And I understand Bluetooth is a random frequency hopping, spread spectrum frequency hopping. So how would you pick up these side artifacts on Bluetooth, given that the carrier frequency is at a random place at any one time?
Yeah, so just to briefly repeat this, like we are attacking, or we showed an attack on Bluetooth, and Bluetooth deployed frequency hopping as optimization to carry over the signal. And how would we deal with that?
So the idea is that each time there is a carrier on, it's like it's opening a window over what's happening on the chip and we can listen to it. So if this carrier changes over time because of hopping, what we could do is listen on a wider bandwidth and demodulate each of the carrier, the one which is on at a given instant in time, or even use multiple receivers really in parallel tuned onto different frequencies. The point is that we know which they are. And actually talking about this, there is a related project that we did in the group which used parallel receivers to cope with frequency hopping when sniffing the Bluetooth packets. So we're pretty confident that we could apply those techniques to make the attack working also in those conditions. Or we could even just listen to one single carrier like we do now, but it would take more time because the window would be on, let's say, for a smaller amount of time. So we would have the window over the encryptions would be rare.
So
just once, oh, sorry.
yeah, so the clock frequency, though, the 64 megahertz is invariant at all times. Did you look at how far that propagates? Obviously, right next to the chip, you could see it, but does it go any distance at all? Did you look?
So the question is whether the clock frequency, like the 64 megahertz leak it well, like how far does it propagate? And
well, for conventional side channel attacks, we looked at literature for the values they declare. Well, with our experiments, we saw something interesting is that actually that frequency propagates to the radio part, and it's amplified by the amplifier of the radio. So thanks to that, when we were turning the radio on, we were able to look at that signal from a distance, I don't know, for example, of some tens of centimeters. And when the radio was off, we would have had to use, small coil antennas and amplifiers that were not necessary in the case of the transmission on. But to go up to 10 meters, we had to move to the main frequency. And the reason is that at that frequency, the components in the circuit, in the system, are meant to transmit. So the power into play, it's bigger.
Okay, thank you.
Yeah, and now just a short addition like that we attack Bluetooth in this specific instance is rather due to historic reasons or due to chance, because that was the first chip where we actually could easily see something. And after we got that working, we saw indications, like we didn't 100% confirmed like the same leaks, but we saw indication of those leaks also, for instance, on Wi-Fi chips. But this is something we will investigate in the future.
Hi, question over here.
Yes?
For the future steps, just out of curiosity, have you guys researched into picking this up not with an SDR, but maybe with like a phone as well? Or would that be possible?
So the question is, if I understood it right, whether we just want for the future work only go to STR or also will try to like enable normal COTS hardware like a telephone to pick up those signals and noise. And so we were not really planning on doing that, and I don't know if it's possible, to be honest.
Yes, the SDRs and the lab equipment, so like spectrum analyzers and so on, are easier to use for automating the trace collection and so on.
Thank you.
Hi, thanks very much for talk. First of all, cool. But then I had actually like a long list of questions, but I'll just ask one right now and maybe they can talk later. If I understand correctly, you've only attacked a software version of AES, right?
Okay, so we just got the sign that we are out of time, like looks like we're done. We will come and talk to you, or just come here and we will see in the wrap-up room.
Excellent.
Sorry for that. And then we can also go through the full list. And once again, thank you all.
Thank you.